All right. This lesson will be the last lesson on exponential function. What we will do is we are going to start sequences tomorrow. So sequences will probably take us about 2.5 weeks, and then it will be all calculus. So last bit on exponential, and we're going to talk about how we use exponential functions to actually model certain real life situations. So hopefully by the end of the lesson, you should be able to recall the general form and exponential equation and its graphical features. You should be able to use a table of values to derive an exponential rule. Now, you need to be able to examine practical contexts that rely on exponential growth and decay models, including finance, population, and temperatures, and so on and so forth. There are many things that you could use, and then use ClassPad to solve, graph, and analyze exponential growth and decay models. All right, let's have a quick look. One of the things that you can really use exponential function is population. Although you can see that around probably here, this bit here, it looks as if it is linear. However, if you actually cut this part off, all right? If you cut this part off, right, you may see that little bit parts of it are all pretty much close to exponential function. Here, there's actually an exponential growth. But somewhere around here, if you just actually, like I say, just take a snapshot of it. This is actually a really, really long time from 2.5 million years ago to 2025. All right, 2025 is a prediction. So think about if you use exponential function to look at population, especially human populations. Yes, you do get exponential growth, but if you're thinking about modeling population, you could maybe restrict it to maybe 50 or 60 years. That's what I do when I was doing a lot of planning, is restricting the population to about 50 years into the future, so I can assume that the population actually is growing at a steady rate. And you can see that exponential function, the start of it is actually pretty, you can use linear to estimate the first bit of it. All right. Now, a typical bacterial growth. You can see that if you are growing a bacteria in the lab, there will be a sort of lag time for the bacteria to grow, and then this is what you call the exponential phase. And then there's a deceleration phase because you're restricting it in a small petri dish, and by the time it gets up to saturation phase, it will actually be tapering off. And then it will start dying down again, and then go up again. So this is actually a typical bacterial growth. You model it, the exponential growth around here, and then you don't actually need to model that, just around here. Use the exponential for this bit here, the exponential phase. So another thing you can look at is how we could treat bacteria in a lab. So I got this from internet. This is where a petri dish full of bacteria and whatnot. And what they did was to treat that with different concentration of, in the lab, concentration of antibiotics, and see how long it will take for the bacteria to halve, and then how much it will take to halve again until that's none. So that is actually an exponential decay. So for example, if I model that, the situation, I start off with about 200,000 bacteria, and then after an hour it's reduced to 100,000, half of it, another half, another half, another half, another half. So this is actually an exponential decay. All right, and scientists uses that sort of information, the exponential decay of carbon, to do carbon dating. Now, the generalized equation, y equals to y naught times a to the power of x, where a is greater than 0. All right, a is a ratio. So y naught is the initial value of y, that is the y-intercept where x equals to 0. X is the independent variable. Generally, in our case, we look at time. A is the multiplying constant, or the ratio. And if A is greater than 1, y grows exponentially. If A is between 0 and 1, y decay exponentially. So recognizing that sometimes A could be greater than 1, A is between 0 and 1. It will never be 1, because if it is 1, it will just be a flat line. Alright? And A can never be 0, because it will be always 0. And if it is less than 0, it is not exponential function at all. Alright, now let's start to look at the example. A bacterial colony has about 2,000 bacteria. The number of bacteria triple every day, assuming that the growth continues this way. Okay, so we know that that's initial, 2,000, and it triples every day. Alright, what is the multiplication factor then? 3. Alright, so what we're going to do is I will define a few things. Let B be the number of bacteria. Alright, hang on. Alright, I need to change the attendance as well. I have got Monty and Wesley. Alright. So we need to define B as the number of bacteria in the colony. Alright. And T equals to time in days. Right. What you really need to do is, when you define your variable, make sure that you define it precisely. So what I would say, for example, this B is the number of bacteria in the colony. We are talking about the bacterial colony, not just B equals to bacteria. It doesn't mean anything. It has to be B equals to the number of bacteria, and then T equals to time in days. All right. Make sure that you know the units. And now we know that it triples every day. You can use this. So you know that A is 3 or R is 3 if there's the ratio. It triples every day. So we know A equals to 3. And the initial value B0 equals to 2000. So if you could write, whatever you call it, you could start thinking about how the bacteria will be in after 60 hours. 60 hours, how many days are there? Thank you. 2.5 days. So the number of bacteria will be B0 times 3 to the power of 2.5. Alright? Will be 3 to the power of 2.5. Therefore, that will be 2000 times 3 to the power of 2.5. Yeah? Alright. Let's, my calculation is, that would be B, the equation. I forgot to write the equation. B equals to B0 times 3 to the power of T. Alright? So that, if you use your calculator, it should be 31176.91. How would you actually give the answer? Round it. So it doesn't matter. Alright, if you give me as 31,000, I'll accept it. If you give me as 31100, I will accept it as well. The reason is, it's really hard to count the number of bacteria. You always estimate. So what you can say is, there will be approximately 31000 bacteria in the colony. Alright? That's probably the best way to answer it. Approximately. Alright? Even if you give me the number 31177, I can't fault you because that is where you get your equation from. As long as you don't give me the decimal place. Alright? So the next bit, how many bacteria will be in the colony after 5 days? So B will be equals to 2000 times 3 to the power of 5, which is 48600. Alright, that's how I did it. So first I actually defined the variables. Then I wrote down the equation. I should have written this one down first. The equation, then work out the number of, then work out T. Alright? Now let's try the second one, please. The amount of air left in a leaking spaceship is decreased by 30% every minute, and the pressure decreases proportionally. Alright? So decreased by 30 minutes, pressure decreased proportionally. When the leak first occurred, the pressure was 105 kilopascal, and what will be the pressure after 6 minutes? Alright, let's think about a question like this. What are we looking at? Yeah, the pressure in the vessel. And what is the time? Minutes. Alright, so it's every 6 minutes. So I'm going to let P equals to the pressure in the spaceship. Now, make sure that you state the unit, kilopascal. And T equals to time in minutes. Alright, so we can actually, right, what is the decaying factor? What's the decaying factor?
0.3.
0.3 and 0.7. Why? Why? Why 0.3? All right. Here, 30% is. Look, read the question carefully. It's decreasing by 30% every minute. How much is left in the 7? Thank you. So the multiplying factor is 7. It's not 7. It's a 0.7. Equals to 0.7. Correct? Yeah? So now, because this is 1 minus 0.3, 30% equals to 0.7. So whatever is left in the spaceship, P naught is 105 kilopascal. All right? So therefore we can write the equation P equals P naught times 0.7 to the power of T. Okay? Or hang on, P naught is 105 times 0.7 to the power of T. All right. So therefore, when T equals to 6, P should be 105 times 0.7 to the power of 6, which is 12.35. So the pressure after 6 minutes is 12.35 kilopascal. All right, let's try example 3, please. 2 more examples, then you can work on the problems. So the population of mice in a rural town, P. So this time P is already defined for you. You don't have to define P. At time T years, again, it is defined for you, so you know what T is. You don't have to define. After 1st of January 2015, it's approximately modeled by the rule P equals 25001.5 to the power of T. So everything is defined for you in this question. You don't actually have to define it now. All you need to do is be able to interpret. Okay? So think about T years after 1st of January 2015. Therefore, when you state the number of mice in the town of January 2015, is when T equals to 0. Right? So the start P0 will be 2500. State the number of mice in the town on 1st of January 2015. So it's 2500. Right? State the annual population growth rate. What is the growth rate?
15%.
Thank you. It's because it's 1.15. 1.15 equals to 1 plus 0.15. Therefore, part B is 15%. Alright? So predict the number of mice in the town on 1st of January 2020. So what would T be? What would T be? 5 years. Thank you. So therefore, you know P equals to 2500, 1.15 to the power of 5, which is 5028.39. So the way I would answer this question is there will be approximately 5030 mice in the town. Now let's discuss part B. According to this model, describe what happens as T approaches infinity. Realistically, is this likely and justify it? Would it be likely?
No.
Why not?
Mice die.
What else?
Mice can't regrow.
Yes, but it is growing. The model is telling me that it's growing. So as T approaches infinity, what would the number of mice approach infinity? Yes or no?
Yes.
Alright. If you give me yes, give me a justification. How would you justify it? Why is it realistic? You're going to be able to argue your case. Now this is a bit that which is not, it's part of maths, but it's how you're going to argue your case. Yes?
It's not realistic because
Hang on, listen please.
it's not realistic because like the reason really support certain number of mice.
Very good. So it is not one reason. It's not realistic because there's a certain amount of resources in there that will support the mice. Number two, there's another reason as well if you think about it. If you are in a rural town, would a human being be intervening and trying to get rid of the mice? Poisoning and doing all sorts of things? It would happen. So really in this sort of part D, you've got to think about a reason. Now the way of answering this question, this sort of question, you always must state yes or no. Alright? Is this realistic? So when you answer this sort of question, the first bit you should say is this model is not realistic. Alright? Generally it will be a 2-mark question answering that. State it whether it's realistic or not. If it is realistic, why? If it is not realistic, why? So 1 mark is given to whether it's realistic. Alright, state that. 2nd mark is your justification. So any sort of justification, you will get another mark in terms of answering a question like this. Yeah, I'm not going to answer that for you. What I'm going to do is I am just going to write down a couple of comments as it. What am I doing? Alright, so what I would do is I'm going to write the not realistic. State your argument. Now, if you could argue that it is realistic, I will accept it as well if it is reasonable. Alright? This way you've got to think. Now, the next one. This is probably one of the harder questions that you may get. The population of a particular endangered species or animal is declining exponentially. The population in 2000, 2005, 2010, and 2013 were thought to be as follows. By what percentage is the population declining each year? Now, from here to here, that is 5 years, correct?
Yes.
And here to here is 5 years. So what you actually want to find is the percentage declining each year. So how are you going to do it? All right. Now, again, I'm going to define, because nothing is defined for you. Let P be the population of the endangered species. All right. Define that. And T equals to time in years. All right. Now, what we want to find is the population declining each year, which is, let's define R. Let R be the declining factor or decaying factor. All right. So we can actually write the equation P equals to P naught R to the power of T, where P naught is 5760 times R to the power of T. All right. How can we do a question like this? So what we start off with, we can go to P5 equals to 5760 R to the power of 5. All right. So P5, you know that P5 is 4460 equals to 5760 R to the power of 5. Therefore, R to the power of 5 equals to 4460 divided by 5760. Question like this, you have to use your calculator, and I worked out R to be 0.9497, which is approximately 0.95. Now, are you going to be satisfied with this? No. Why not? Are you going to use this straight away? No. You can't. You actually got to check what happened in between here and here, or in between here and here, to confirm that the decaying factor is correct. So I could actually use P equals to P10 equals to 5760 R to the power of 10, and P10 is 3450 equals to 5760 R to the power of 10. R to the power of 10 equals to 3450 over 5760. So R equals to 0.9500, approximately 0.95. So you confirm that by looking at three of them, you confirm that R is 0.95. Of course, if you like, you can use those two as well. Okay? Again, the ratio would be R to the power of 5 is 3450 divided by 4460. If you use that, it should give you about 0.95. All right. So therefore, what percentage is the population declining each year? Is 5%. Thank you. So the answer A is 5%. All right. So can you predict the population for this animal for the year 2015? So 2025 is 25 years. So therefore P25 equals to 5760 times 0.95 to the power of 25. So which gives me about 1597.26. The population will be approximately 1597.26 5 or 1600. I use 1600. Even if you give you 1590, could be 1600. That's fine. All right. 1590 is more in line with the answer here. They all have 0, and it's got the two numbers there rather than rounded up to 0. 0, 0. All right. So think about how you answer a question like this. How you could actually use this information to find your decaying factor or your growth factor. All right. I'm going to stop here and just quickly reflect on your learning.